Hello, we're gonna talk about chapter 11, combined heat and power system. Okay, this is a little bit different from combined cycle, as we will see next. So, the thermal efficiency of our power plant, we need this number to be as high as possible, or we want the heat rate, the BTU per kilowatt hour, to be as small as possible because it's the inverse of the isothermal. So over here he's saying that a traditional gas-fired steam turbine would have that heat rate, right, from 10,000 to 15,000. But in over here in Jenks steam power plant, when they hit 10,000, they think that's horrible. They always want to be less than 10,000, right? They want to be 9,000 and something. So the way to reduce that heat rate is to increase your efficiency. And the way to increase the efficiency is by having a combined cycle. And we saw that in the previous uh, chapter when we have a gas turbine exhaust that we would use it to run a steam power cycle, right? And so you get work from this one, work from the other one, and you'll end up having higher efficiency, therefore very low BTU per kilowatt hour for natural gas combined cycle. So that is the our sketch for a combined cycle. You can see how the compressor and the turbine and the combustion chamber, those guys are running a generator, and that's where you generate the energy from the gas turbine. The exhaust, however, is too hot to throw away, so rather than wasting that exhaust, they send the exhaust to a steam boiler. That boiler makes steam for a Rankine cycle waiting over here. Sometimes that exhaust is not hot enough or good enough or have energy large enough to run the steam heat recovery steam generator, so they add more burning, right? That's the example we saw with the supplementary firing, and we learned how to calculate how much additional fuel we need to burn over here, right? So that is the typical combined cycle. Exhaust being used with or without additional firing in order to generate steam. So even with a combined cycle like this, and even with with efficiency as high as 65%, over here is basically showing that when you use burning fuel to start with, natural gas, coal, whatever your fuel is, you have efficiency for that conversion. Not all the all the fuel chemical energy is released. Why? Well, you still need stuff in the stack, right? And so that is still need to be hot so that you wouldn't condense the water vapor. So you're gonna lose energy in the exhaust. You lose energy in maybe the combustion is not complete, right? So 91%. And so with like an efficiency as high as 55% over here, you will end up only with 50% because 55 of the 91. And so now only 50% is being transferred into electric power, right? And that electric power you lose a little bit, not much in the electric wiring all the way until it go to the city, and then inside the city you lose a little bit in all the wiring to the end consumer over here. So out of the 100% that we burn in the furnace, we get 40% electricity going to our homes. So what that means? It means that there is a lot of energy that is being wasted in the exhaust, right? Whether exhaust of a gas turbine by itself, that will be a lot, or whether in the exhaust of the gas turbine and the heat recovery boiler. And in that cycle also there is the condenser, right? And the condenser is being cooled by another cooling tower. So all this energy that we waste, right, is responsible for that loss of energy. So they saw that, well, that's not nice, and we need to recover some of that energy, the thermal energy that's wasted in the condenser and wasted in that chimney. So what do we use this energy for? Well, it's not good for making more electric power, because the steam turbine did its job and recover as much as it can, right? And the rest is basically just stack losses and condenser losses. But that energy lost in the condenser is actually good for heating, right? So how do we do heating right now? A lot of people do heating by electric power, all right? So think about the your home HVAC system. When you turn from summer to winter, and you basically turn it to heating, most of the time he's using a heat pump, and that heat pump is using electric power, right? And maybe you have a small furnace like me on top of the in the attic, that basically when the heat pump does not handle the load by itself, he basically kick in the natural gas in that small furnace, and you get the extra heating, right? A lot of you also cook on electric stove, right? And our oven is electric. So there's a lot of heating application that we use electricity for. And as a mechanical engineer that know this fact, that know that the natural gas that we burn in the steam power plant or the combined cycle power plant in Oaso came only 40%, let's call it 50%, only 50% made it to us as electricity, and the other 50% is basically sent into the river and in the air. That 50%, I mean, that electricity it's criminal, almost criminal to use it for heating, because we could just got heating by burning natural gas ourselves rather than using electricity to turn it into heat, right? Because that electricity again come with 50% efficiency, right? So every joule that you would use in your electric stove for electricity, there is another joule of natural gas fired in the steam power plant that's being waste to the sky, right? So have you used natural gas directly into your stove, you would use 1 joule rather than 2 joules of electricity, right? If you burn electricity or use electricity. Does this make sense? Right? Because 1 joule of electricity in the stove has to have another joule of natural gas, an extra joule of natural gas that's being wasted in the stack and in the condenser of the power plant. So especially that electricity is not cheap, and maybe we have cheap electricity in Oklahoma at 11 cents, but look at this is the 2016 prices. Hawaii, they were paying 27 cents per kilowatt hour. Okay, so the average in the United States at 2016 was 12 cents per kilowatt hour. So in Oklahoma, we are a little bit lucky, we pay a little bit less than the average. Some states are even luckier, but I mean still it's 9 cents, it's not like for 5 or 4 or something. And some they pay a little bit more. And on average, every house in the USA pay like $1,300 worth of electricity every year. Some pay a little bit more when it gets colder, or when they don't have that much natural resources. Okay, it's not that cold in South Carolina. Maybe in Connecticut in the winter. And some pay less. Okay, smaller household, not that much requirement for air conditioning. Okay, but anyway, the price of electricity is a big deal, and so to trade this idea that in order to use electricity for heating purposes, in order to see is that okay or not, are we really doing too much waste, you can do this by calculating the difference between the cost of natural gas and the cost of electricity. Then you realize that, man, I shouldn't really buy that electric stove, I should buy a natural gas fire stove. So how do we calculate this? We want to calculate the cost of natural gas. How much dollar per BTU? 10 to the power 6 BTU, so 1 million BTU. So they could charge you per CCF, cubic feet, or they could actually charge you just directly per BTU. So the bill would come how many BTU did you use, and so that's the equivalent of how much what is the heating value of burning that natural gas in your furnace. But the point is, after a bunch of conversion, you'll be able to calculate what is the price for 1 million BTU. So $9 for natural gas, and the cost of electricity, 12 cents per kilowatt hour in this example. In Oklahoma, it's like 11 point something. So you not, in order to compare apple and apple, we need also calculate the electricity in terms of BTU, not kilowatt hour. Okay, and so what is the conversion? 1 kilowatt hour is 3,412 BTU. Okay, so and then since we wanted it per 1 million BTU, you do the conversion and you get what is the price of electricity per 1 million BTU. Okay, work the math yourself, it's pretty easy. So burning natural gas, 1 million BTU of natural gas will cost you $9, and 1 million BTU of electricity, the equivalence of kilowatt hour, will cost you $35. Okay, so that's what you lose if you use an electric stove rather than a natural gas stove top. So now the difference between those two numbers, they have an interesting name. It's called the spark spread. Okay, so in order to do that spark spread, it's how expensive the electricity with respect to compared to natural gas. That's why we want to do that conversion. In case you are wondering why he calculating the electricity per BTU, because I want the price to be apple and apple, basically. 1 million BTU, 1 million BTU. So when you do this, you get something called the spark spread. So that spark spread tell you how valuable the electricity is, and it also tell you where is what is the profit margin for an electric power company. So if you are planning to run your own electric company generating electricity and sell it to consumer, that spark spread is your profit, right? You're gonna pay this to the natural gas company that supply you with natural gas. And by the way, in Jenks over here, they have 3 natural gas pipeline coming to their power plant from 3 different companies. And so they choose to open the line depending on the price. So they look at the prices and they say, well, this company is selling us cheaper than this one. Let's use this one today. Okay. So that difference is how much money they can make. Okay. And so obviously that, hopefully this number is large enough not only to pay for the operational cost, but also to pay for the initial cost, right? The power plant cost them, you know how many millions of dollars? $1 billion for a big power plant, and they need to be able to recover the price and make profit during the lifespan of the power plant, so that then it become a good investment, right? Very good. So that spark spread obviously will depend on the local price of electricity, and you can see he's comparing here different places, New York and some West Coast over here, Chicago, right? Somewhere here near the Gulf. And you can see in some places, of course, it's vary with the season, so the electricity price varies depending on how much people need it, and if there is a lot of AC running and it's peak time, they can charge you more, right? And so then the spark spread, the difference between what does electricity cost compared to how much natural gas cost, will end up being really, really big. So here come the idea of combined heat and power system. So a combined heat and power system is basically saying that, well, electricity is really expensive, right? And I cannot use my all that electricity to heat my building, for example. That would be insane, right? So I should probably use direct heating for my heating application. For example, I could just like have a boiler, right? And generate heat from it by burning natural gas. Big furnace for my hotel or my hospital. So now it makes sense then if you are also using electricity all the time and you have a lot of heating all the time, rather than just buying electricity and having your own boiler for heating, that you would have your own power plant in the building. And so the point of a whole power plant in your building is that, again, burning natural gas in the power plant, in the small power plant, come with 91% losses, 91% efficiency, 10%, 9% losses in the burning itself. And then with your electric generation, you will get an efficiency of 50%. Okay, that's a good efficiency, amazing efficiency, 50% uh, electric generation. Now the other 50% that was going to be lost in the condenser in the big main central power plant across the river, now since we have the power plant in our own hotel or our own hospital or our own campus, like the OSU, for example, campus in Stillwater, then we can use that 50% losses for our own heating. Okay, and so when you do this, then the natural gas that you are paying for, right, you end up having an 80% efficiency of it, some electricity and some heating, right? So 50 and 30 or 30 and 50, depending on the system that you're gonna use. So that is the idea behind combined heat and power generation. So now, in order to convince the hotel manager or the hospital administration that this is a great idea, there's certain conditions that need to be satisfied to make that worth the effort. Okay, what's the effort? You're gonna buy a steam power cycle and put it in your hotel. It's expensive, right? And it doesn't have to be a steam power cycle. I mean, you can just buy a small gas turbine, right? A small gas turbine, and then the exhaust, you will use it for heating. That would be combined heat and power production. Well, that gas turbine, it's gonna cost a lot of money. So in order to justify this to the administration or to the budget office in your organization, you have to have few conditions. What are those conditions? One, he's basically saying that you need heating all the time. This is not like we only need heating when we cook the food for the guests and we turn on the furnaces. No, for having a whole power plant sitting in your premises, you need to have continuous use of natural gas, and there is something called the usage factor that we can calculate. And the usage factor is how much energy you are producing and the peak kilowatt hour that you need. So the peak kilowatt hour is that when everyone turn on their AC, that will cause the kilowatt to really increase, how much kilowatt we are consuming right now. And the kilowatt hour is all over the months, or all over the billing period, how much did we use. So if this number is close to 1, like he's showing over here, that means that we turn everything on all the time. In that scenario, it's perfect. This is a really good candidate for having your own combined heat and power cycle, right? Because you are gonna use it all the time. You are not gonna turn it off and on. You are not gonna generate more electricity that one would need, and therefore you will basically just have to store it or sell it back or something. So he's basically saying there are 3 things that need to be satisfied. You will have a use for electricity generated, and that can be shown by the usage factor. There is a use for the thermal energy recovered. Again, he's saying that you actually need that heating all the time. Again, you can measure this by the usage factor. Is it 0.7 or 0.9 or 0.3? Like only you need just heating only at night, and that's it. And sufficient spark spread. Why? Because that spark spread saying that electricity is way expensive than heating, and so people can make money by generating their own electricity. right? Very good. So he's showing this over here. He's calculating the cost of natural gas, the cost of the kilowatt hour, and doing the conversion again so that he can have apple and apple, BTU and BTU, calculating the spark spread. And then if there is like those two usage available, then yeah, that makes sense. Let's build our own part.